ऑटो वाले को हमने 800 कर दिया था। 40 से 45 हज़ार। पर इतना क्यों है? पर इतना ही बजट में आप स्कॉर्पियो करते तो लोग भी खुश। ससुराल में बताइए आपके पापा भी ये बताइए कि आप 800 में मैंने स्कॉर्पियो को सकते हैं और बिना में सकते हैं तो हमने भाई सजेस्ट कर दिया किसको कितना ऑटो रखना पैसा। जिस दिन फॉर्म बनाना शुरू किया था उससे एक बात बोली थी कि छोटे फॉर्म पर सारी बेसिक चीजें दिखाई जाएगी। इसके अलावा फिर अपने फॉर्म पर कोशिश काम में रेडी हो जाएंगे। आपका फिलहाल तुम्हारे बर्थडे वन के हिसाब से कौन सी हमारी खेलने वाली जल्दी से कवर जल्दी का वीडियो का टाइमर वाली है यार। तुम्हारे बर्थडे वन I tried something that's a little over the Photoshop and in turn web browsers
could represent that same color white with FF. And let's just do a few others. Here is red. And it turns out that red is a whole lot of red, 255, but no green, no blue, or AKA FF0000. So there's perhaps a pattern here emerging. Here is green, 0, 255, 0, AKA 00, FF00. Red is a whole lot of red, 255, but no green, no blue, or AKA FF0000. So there's perhaps a pattern here emerging. Here is green, 0, 255, 0, AKA 0. Represent that same color white with FF. Probably are familiar. Some of you have already made web pages before, and you know a little bit of HTML and CSS. You probably are familiar with this kind of syntax, like a hash symbol, and then 6 or sometimes 3 digits thereafter. And if we look at a few different colors here, for instance, here might be the representation of white. Now the R, the G, and the B values went way up from 0 to 255, 255, 255. Or alternatively, it looks like Photoshop, and in turn, web browsers could represent that same color white with FF. And let's just do a few others. Here is red. And it turns out that red is a whole lot of red, 255, but no green, no blue, or AKA FF0000. So there's perhaps a pattern here emerging. Here is green, 0, 255, 0, AKA 00, FF00. Or lastly here, blue, which is no red, no green, but apparently a lot of blue, 255 again, AKA 0000, FF. Now, some of you, again, might have seen this notation before, these zeros and these Fs and all of the numbers and letters in between, but this is another form of notation. And in fact, we'll explore this today. Really is just a precondition for talking about some other concepts, but the ideas ultimately are really no different. What we're about to see is a different base system, not just binary, not just decimal, but something we're about to call hexadecimal. But first, recall that with RGB, we previously did the following. Any RGB value, red, green, blue, just combine some amount of red or green or blue. So here we have 72, 73, 33, which in the context of an email or text, of course, said what? A couple weeks back? Just hi with an exclamation point. But in the context of a Photoshop-like program, this might instead be representing collectively this shade of yellow, for instance, when you combine that much red, that much green, that much blue. So here's the same idea. If you've got a lot of red, no green, no blue, together that's going to give us red. If you've got no red, a lot of green, no blue, that's going to give us, of course, green. If you've got no red, no green, a lot of blue, that, of course, is going to give us blue. So there's a pattern emerging here where apparently 0, 0 is none, as always, and FF is apparently a lot. And it's maybe somehow equated with 255, at least per that Photoshop screenshot. Meanwhile, if we combine one last one, a lot of red, a lot of green, a lot of blue, that's actually going to give us a single white pixel like this. All right, so think back. Here was binary. In the world of binary, you had just 2 digits, 0 and 1. Could have been anything else, A or B, X or Y, but the world standardized on these numerals, 0 and 1. In our world's decimal system, of course, you have 0 through 9. As of today, though, we're going to start using hexadecimal sometimes in the context of images and also files, just because it's a convention. There's some conveniences to it, where now you're going to be able to count up to F in a notation called hexadecimal, from 0 through 9. Then you keep going to A to B to C to D to E to F. The idea being each of these, even though it's weirdly a letter of the English alphabet, it's still just a single symbol. It's not 1, 0 for 10 or 1, 1 for 11. All 16 of these values, these digits, so to speak, are indeed still just single symbols. And that's a characteristic of just using this other notational system. So how do we get from 0, 0 and FF to something like 0 and 255 respectively? Well, this hexadecimal system, aka base 16, just does the math from week 0 and really grade school a little bit differently. For instance, if you have a number that's got 2 digits, or hexadecimal digits as of today, the columns are just a little different. Instead of powers of 2 or powers of 10, which we saw for binary and decimal respectively, it's powers of 16. So if we just kind of do the math out, that's the 1s column, this is the 16s column, and so forth. Things get actually pretty big pretty quickly in this system. But now let's just consider how we would represent familiar numbers. If you've got 2 hexadecimal digits, for which these hashes are just placeholders, 0, 0 is going to mathematically equal the decimal number you and I know, of course, as 0. Why? Same thing as week 0. 16 times 0 plus 1 times 0 is the number you and I know as 0. And we can count up from here. This in hexadecimal would be how a computer represents the number we know as 1. It would be 0, 1 in this case. This would be 2, 3, 4, 5, 6, 7, 8, 9. In decimal, we're about to go to 10, but in hexadecimal, to be clear, what comes next? So apparently A, so 0A, 0B, which is now 10 or 11 or 12, 13, 14, 15. So using hexadecimal is just kind of an interesting way of using single symbols now, 0 through F, to count from 0 through 15. And we'll see why it's 15 in a moment. But as soon as we get to F, anyone want to conjecture how in hexadecimal, aka hex, do we now count up one position higher? What comes after 0F in hexadecimal? So 1, 0. It's the same kind of thing. Like once you're at the highest digit possible, F, or in our decimal world, it would have been 9. You sort of add one more, and 9 wraps around to 0. Or in this case, F wraps around to 0. You carry the 1, and voila, now we're representing the number you and I know as 16. And we can keep going forever, literally. This could be 17, 18, 19, 20 in decimal. But let's just wave our hands at it and count as high as we can, dot, dot, dot. The highest we could count in hexadecimal with 2 digits just logically would be what? In hexadecimal, something, something. FF, I heard. So yes, that's the biggest digit possible. So FF is what we have. So how high can you count in hexadecimal if you've got just 2 of these digits? Well, it's the same math as always. 16 times F, aka 15. So that's 16 times 15 plus 1 times F, or 1 times 15. That gives us 240 plus 15 in decimal, the result of which, of course, now is 255. So this hexadecimal system you may have seen in the world of web pages, and if you haven't, we'll get to that in this class in a few weeks, or we just saw in the context of Photoshop, just has this sort of shorthand notation of counting as high as 255, but just calling it FF. Now, it's marginal, but that's like 50% savings of how many digits you need in order to count as high as 255, because in decimal, of course, 255 is 3 digits. In hexadecimal, you can count as high using just 2. And that difference is going to get magnified the bigger our numbers get. Let me stipulate for now, you're going to get more and more savings in terms of just how many symbols you need on the screen to represent bigger and bigger numbers than that. All right, let me pause here just to see if there's any questions thus far on what we've called hexadecimal, which again just gives us 0 through 9 as well as A through F. Any questions or confusion? And if it feels like we're lingering a bit much on arithmetic, we're not really going to see other notations besides this moving forward. These are sort of the go-to 3 in a programmer's world, typically. But there are some others. Yeah? Good question. Does hexadecimal require more storage or less storage than a decimal system? Theoretically, no, because this is just a way of representing information. And we'll see in a concrete example in a moment. But inside of the computer, at the end of the day, you're still storing bits. And using hexadecimal is not using more or fewer bits. Think of this as how you might write it down on a piece of paper, just how many digits you're going to write, or on a computer screen, how many digits you're going to see at once. But it doesn't change how the computer is representing information, because all they're representing at the end of the day is zeros and ones. So in fact, let's go there. If this, a moment ago, FF, I claim was 255, let's just rewind to week 0. And if we wanted to count to 255 in binary, that's as high as you can count, recall, with 8 bits. And there's only a few of these numbers that are useful to memorize. Like 255 is as high as you can count with 8 bits. If you start at 0, there's 2 to the 8th is 256. But if you start at 0, it's 0 through 255. So in binary, recall, if you have 8 bits, all of which were 1s, and I won't do out the math pedantically here, but if I do this plus this plus this, dot, 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 that's also going to give me 255. So this is what's interesting here about hexadecimal. It turns out that an upside of storing values in hexadecimal is that we're going to see the first F sort of represents the left half of all these bits, and the second F, in this case, represents the rightmost 4 of these bits. So it turns out hexadecimal is very useful when you want to treat data in units of 4. It's not quite 8, but units of 4, and that's not bad, which is why if you use 2 digits like I have thus far, 00 or FF or anything in between, that's actually a convenient way of representing 8 bits in total. 1 hex digit for the first 4 bits, 1 hex digit for the second. And again, there's nothing new intellectually here per se. It's just a different way of representing the same story. as before, zeros and ones. So in what context do we see this? Well, we talked about memory last week, and we're going to talk more about it this week. If this is my computer's RAM, random access memory, you can again think of each byte as having a number associated with it, like its address or location. This might be 0. This might be like 2 billion. And so in the past, I described these as just this, using decimal numbers. Here's byte 0, 1, 2, 3, 4, 5, 6, 7, 15. 16 would be here, and so forth. But it turns out in the world of memory, and thus today programming, people tend to count memory bytes using hexadecimal. Partly just by convention, but also partly because it's a little more succinct. And again, each digit represents 4 bits, typically. So what comes after F here? Well, if I think about the computer's memory, I normally might do after F, which is 15, 16, but instead 1, 0, 1, 1, 1, 2, 1, 3. This is not 10, 11, 12, 13, because I claim I'm in the context of hexadecimal now. As per the previous slide, we already started going into A's through F's. So you immediately see here a possible problem. Like, why is this now worrisome if all of a sudden you're seeing seemingly familiar numbers like 10, 11, 12, 13? We didn't really stumble across this problem when it was like all zeros and ones before. Yeah. Yeah, so if you're writing some code in C that's doing some math, you might accidentally, or the computer might accidentally confuse hexadecimal with decimal if they look in some context the same. I mean, any number on the board that doesn't have a letter is ambiguously hexadecimal or decimal at this point. And so how might we resolve this? Well, it turns out that what computers typically do is this. By convention, anytime you see visually 0x and then a number, that's a human convention of signaling to the reader that this is, in fact, a hexadecimal number. So if it's 0x10, that is not the number 10. That is the hexadecimal number 10, which, recall we said earlier, is how you count up to 16. And again, these are not the kinds of things to memorize. It's really just the system for how you think about these things. So henceforth today, we're going to start seeing hexadecimal in a bunch of contexts. When you write code, you might even write code using some hexadecimal. But again, it's just a different way of representing numbers, and humans have different conventions for different contexts. All right, so with that said, any questions now on this building block? But here on out, we'll start using it in some actual code. Any questions? Nothing so far? All right, so let's go ahead and consider maybe a familiar example, something where involving code where I initialize a variable like n to a value like 50 in this case, and then let's start to tinker around with what's going on inside of the computer's memory. In a moment, I'm going to load up VS Code on my computer, and I'm going to go ahead and whip up a program that very simply assigns a value like the number 50 to a variable called n. But today, keep in mind that
एक कौशिक भाई मेरा 3rd ईयर आ चुका है और मैं पढ़ना भी चाहता हूँ ना.
Our variable n, and that value 50 is going to be stored somewhere in my computer's memory. And it turns out today we'll introduce a bit more syntax so you can actually see where things are being stored. So let me click over to VS Code here. I'm going to create a program called address.c just to explore computers' addresses today. And I'm going to do an include standard io.h, int main void, as usual, no command line arguments for now. I'm going to declare that variable n equals 50. And then I'm just going to go ahead and print it out. So nothing very interesting, but I'll use %i, \n, and then comma n to print out that value. Nothing here should be very interesting to compile or run, but I'll do it just to make sure I didn't make any mistakes. Looks like, as expected, it simply prints out the number 50 like this. But let's consider then what this code is doing underneath the hood when it's actually run on your machine. So here we have that grid of memory. That variable n is an int. And if you think back, how many bytes typically do we use for an int? Yeah, 4. So 4 bytes or 32 bits. So if each of these squares represents 1 byte, then my computer somewhere in my memory or RAM is using 4 of these squares. Maybe it ends up over here just because there's other stuff being used elsewhere, for instance. Though I don't really know, and frankly, I don't really care where it ends up, just that it ends up somewhere. So the value 50 is stored here in a variable called n. Even though I've written it as decimal, just like in my code, let me again remind that this is 32 zeros and ones representing that 50. It's just going to be very tedious if we start writing everything in binary, so I'll use the more comfortable human decimal system. System. So that's what's going on inside of the computer's memory. So what if I actually wanted to start tinkering with its location, or maybe just knowing its location? Well, this variable n indeed has a name, n. That's a label of sorts for it. But at the end of the day, that 50 is technically at a specific address. And I'm going to make one up. 0x123. And it's 1, 2.
भाई दया करने की कोई जरूरत नहीं है, मतलब ऐसा कुछ एक मैं देखता भी नहीं हूँ कोई मुझे देख रहा है या नहीं देख रहा है, मैं बस लाइव करता हूँ, पढ़ता हूँ। वैसे तो लड़की लोगों को देखने में आपको शर्म तो आता नहीं होगा। लिंक मांगते होगे वो वाला 19 मिनट वाला, तब तो आपको खराब नहीं लगता होगा, बट मैं कर रहा हूँ तो आपको खराब लग रहा है, राइट?
Because I really don't care what it is. I just want an address for the sake of discussion. So way over here, off.
भूल गया भाई, राइट? याद लो, भूल गया भाई. Keep it up, bro. Thanks for watching, but by the way, thank you, bro. Bro, literally, बात तो सही है, बट आपको ऑप्शन है ना एंड करने का, मतलब हट जाने का, बट आप फिर भी देख रहे हो यार, क्यों? मतलब मैंने तो बोला नहीं आपको, राइट? और आप सब्सक्राइबर भी नहीं हो मेरे, तो क्यों ही देख रहे हो भाई मेरे को? पहला क्वेश्चन तो आपसे पूछना चाहता हूँ, क्या आप गे, मतलब तुम गे हो क्या भाई? छोड़ो, हटाओ.
So I don't really know. And frankly, I don't really care where it ends up, just that it ends up somewhere. So the value 50 is stored here in a variable called n. Even though I've written it as decimal, just like in my code, let me again remind that this is 32 zeros and ones representing that 50. It's just going to be very tedious if we start writing everything in binary, so I'll use the more comfortable human decimal system. So that's what's going on inside of the computer's memory. So what if I actually wanted to start tinkering with its location, or maybe just knowing its location? Well, this variable n indeed has a name, n. That's a label of sorts for it. But at the end of the day, that 50 is technically at a specific address. And I'm going to make one up. 0x123. And it's 123 because I really don't care what it is. I just want an address for the sake of discussion. So way over here off screen might be byte 0. Way down here is byte 0x123. It's in hexadecimal notation just by convention. So how can I actually see where my variables are ending up in memory if I'm curious to do so? Well, let me go back to my code here. And let me actually change this just a little bit. Let me go ahead and introduce, for instance, another symbol here and another topic altogether, namely pointers. So a pointer is a variable that stores the address of some.
भाई क्या छापा है मैंने, मतलब क्या? और किससे छापा भाई, बताओ यार, बताओ किससे छापा मैंने? कौन करता है ऐसे, बताओ भाई. तू मेरे साथ बैठ के पढ़ सकता है CS50, बट नहीं, तेरे को बकचोदी करना है मेरे साथ.
value, the location of some value, or more specifically, the specific byte in which that value is stored. So again, if you think of your memory as being a whole bunch of bytes, 0 at top left, 2 billion or whatever at bottom right, depending on how much RAM you have, each of those things has a location and an address. A pointer is just a variable storing one such address. So it turns out that in the world of C,
भाई कौशिक भाई तुम जीत गए भाई क्यों
there's a couple of new symbols we can use if we want to see what it is we're talking about here. And those two operators, as of today, are these. You can
लाइक मैं लाइव के बाद ही पढ़ता हूँ ब्रो बता चल तू मेरे को बता क्या कंटेंट होना चाहिए बता मेरे को लाइक तू जा जानता है मेरे से तो बता दे क्या करना चाहिए मेरे को और क्या खराबी है इसमें वो बता दे बस
use the ampersand operator in C in a couple of ways. We already saw it very briefly to do ampersand, ampersand, to kind of and two Boolean expressions together in the context of a conditional. This is different. A single ampersand is the address of operator. So literally in your code, if you've got a variable like n or anything else, and you write ampersand n, C is going to figure out for you what is the address of that variable n in the computer's memory. And it's going to give you a number, otherwise known as the address of that. If you want to store that address in a variable, even though, yes, it's a number, like 0x123, you have to tell C in advance that you want to store not an int per se, but the address of an int. And the syntax for doing that, somewhat non-obviously, is to use an asterisk here, a star operator, and you say this when creating the variable. If you want p to be a pointer, that is the address of some other variable, you do int star p. And the star just tells the computer, this is not an integer per se, this is the address of something. That yes is an int, but we're just being more precise. So on the right-hand side, you have the address of operator. As always, with the equal sign, you copy from right to left. Because ampersand n is by definition the address of something, you have to store it in a pointer. And the way to declare a pointer is to specify the type of value whose address you're storing, and then use the star to indicate that this is indeed a pointer and not just a regular. Old int. So let's see this in practice. Let me go back to my own source code here, and let me make just a couple of tweaks. I'm going to leave n alone here, but I'm going to go ahead and initially just do this. Let me say int star p equals ampersand n, and then down here, I'm going to print out not n this time, but p, the variable p. And then even though, yes, it's just a number, and therefore I kind of sort of could use %i for integers, there's actually a special format code in printf for printing pointers or addresses, and that's %p. So now let's go ahead and recompile this, make address. So far, so good. /address, enter. And a little weirdly, but perhaps understandably now, the address in my computer's memory at which the variable n happened to be stored was not quite as simple as 0x123. This computer has a lot more memory, so technically it was stored at 0x7ffcb4578e5c. Now that has no special significance to me. It could have ended up somewhere else altogether, but this is just where in my computer, or technically the cloud server to which I'm connected using VS Code here, that just happens to be where n ended up. And strictly speaking, I don't even need to introduce this variable. I could get rid of p, and I could just say print not just n, but the address of n, and achieve the same thing. You don't need to temporarily store it in a variable. Let me just do make address again, /address, and now I see this address here. And notice if I keep running the program, it's actually moving around. There's other stuff presumably going on inside of the computer. Maybe it's actually randomizing it, so it's not always at the same location. That can actually be a security feature underneath the hood. But moving around this address here.
बताओ कौशिक भाई बताओ प्लीज मैं हूँ तो कुछ नहीं बट बता सकते हो अपना भाई समझो यार भाई भाई समझ के बता दो यार कौशिक भाई सेम नाम है ना हम लोगों का सेम कौशिक कौशिक ठीक भाई मेरे को मान लो यार पीएस कोड खोल देता हूँ क्या जो बार बार देख रहा है क्या देख रहा हूँ भाई hashtag include stdio dot right उसके बाद int main void equals to 50 तो बार बार देख रहा है क्या देख रहा हूँ भाई मतलब परसेंटेज है selection Yep. There. Dot. Oh, क्या देख रहा है चलो
And notice if I keep running the program, it's actually moving around. There's other stuff presumably going on inside of the computer. Maybe it's actually randomizing it, so it's not always at the same location. That can actually be a security feature underneath the hood. But this happens to be at that moment in time where that value is in memory, quite like our picture a moment ago. All right, so let me pause here to see if there's now any questions on what we just did. Yeah.
कितना यूज जा रहा है अभी? हाँ?
ऐसे था
क्या बोल?
देख तो
Really good question. Is there any way to control where something is in memory? Short answer is
क्या क्या कितना यूज है?
ऐसे
ये क्या कर रहा है?
yes. And this is both the power and the danger of C. And we're going to do this today and make a few deliberate mistakes, because with this power of going to or getting the address of any variable, I could just arbitrarily right now write code that stores a value at like byte 2 billion or 0 or anything in between. But that also means potentially I could start kind of looking around at all of the computer's memory, even at things that I didn't put there, maybe other programs, maybe other parts of programs. And indeed, this is a potential security threat. If suddenly you're able to just look anywhere you want in the computer's memory. Now, I'm overselling it a little bit, because nowadays in this decade, there are some defenses in place in compilers and in our operating systems that do hedge against this a little bit. This is still a very frequent source of problems. And later today, we'll talk briefly about things called Stack Overflow, which is not just a website. It is a problem that you can encounter. Heap overflow and more generally buffer overflows. There's just so many things that can go wrong using this language called C. And if any of you have encountered a segmentation fault yet, I think we saw a few hands for that already, you touched memory that you shouldn't have. And odds are you did it most recently by going too far in an array, going to the left or negative in an array, or somehow looking at memory you shouldn't have. And we'll explain today why it is you were able to do that.
like बोल रहा है कि क्यों करता है कौन सा क्लास में तू बट ट्वेल्व में तो बोर्ड नहीं होता मुझे सी नहीं होता मुझे होता है
Other questions on these primitives so far? Yeah, from Carter? Good question. Earlier we used star p. Let me rewind in time to the previous version of this code where I actually had a variable called p. Just like with variable declarations in the past, once you've declared a variable to be an int, a char, a bool, or an int star, aka a pointer, you don't thereafter keep using the word int or now the star. Once you've declared it, that's it. You only refer to it by name. And so it's very deliberate what I did here, saying that the type here is int star, that is a pointer to an int. But here I just said the name of the variable as always. I didn't repeat int, and I also didn't repeat star. But at the risk of kind of bending one's minds a little bit, there is unfortunately one other use for the star operator, and that's as follows. If you want to print out not the address of something, but what is at a specific address, you can actually do this. If I want to print out the integer via %i that is at that address, I can actually use the star here, which technically contradicts what I just said, but it has a different function here, different purpose. So let me go ahead and do this in two different ways. I'm going to leave this line of code as is, but I'm going to add another line of code now that prints out what apparently will be an integer in a moment. So %i\n. And I could cheat, and let me just do n for now. So there's really nothing special happening now. I'm just adding a sort of mindless printing of n. So make address, /address. There's the current address of n, and there's the value of n. But what's kind of cool about C here, too, is if you know that a value is at a specific address like P, there's one other use for this star operator, the asterisk. You can use it as the so-called dereference operator, which means go to that address. And so here what we actually have is an example of a pointer P, which is an address like OX123 or OX7FF and so forth. But if you say star P now, you're not redeclaring the variable, because I didn't mention int. You're going to that address in P. So let me recompile this now. Make address, /address. And just to be clear, what should I see? I'm first going to see the pointer itself, OX something. What's the second line of output I should presumably see now? Just shout a little louder. So I'm hearing 50. And that's true because if you figure out the address of n, and print it in line 7, but then go to the address of n, aka p, that's indeed going to just show you the number n, the value of n again. All right, any questions now on this syntax? And I will concede, I think this is confusing. The fact that we use the star for multiplication, the fact that we use the star to declare a pointer, but then we use a star in a third way to dereference the pointer and go to the pointer. It's just confusing, honestly, but with practice comes comfort. Yeah? Good question. Do you, when you are using the ampersand operator to get the address of something, the onus is on you at the moment to know what you are getting the address of. Is it a string? Is it a char? Is it a bool? Is it an int? I wrote this code, so I know in line 6 that I'm trying to get the address of what is an integer. In line 8, you don't have to worry about that. Good question. Notice in line 8, I didn't tell the computer, other than the %i, what kind of address I'm going to. But I did already. In line 6, I told the compiler that p, now and forever, is going to be the address of an int. That's enough information in advance so that printf, or really the language C, still knows on line 8 that p is a point. Confusing. The fact that we use the star something, what's the second value, that address? So %line of code now that prints out what apparently will be an integer in a moment. So %i\n. And I could cheat, and let me just do n for now. So there's really nothing special happening now. I'm just adding a sort of mindless printing of n. So make address, /address, there's the current address of n, and there's the value of n. But what's kind of cool about C here, too, is if you know that a value is at a specific address like p, there's one other use for this star operator, the asterisk. You can use it as the so-called dereference operator, which means go to that address. And so here what we actually have is an example of a pointer p, which is an address like OX123 or OX7FF and so forth. But if you say star p now, you're not redeclaring the variable, because I didn't mention int. You're going to that address in p. So let me recompile this now. Make address, /address, and just to be clear, what should I see? I'm first going to see the pointer itself, OX something. What's the second line of output I should presumably see now? Just shout a little louder. So I'm hearing 50, and that's true because if you figure out the address of n and print it in line 7, but then go to the address of n, aka p, that's indeed going to just show you the number n, the value of n again. All right, any questions now on this syntax? And I will concede, I think this is confusing. The fact that we use the star for multiplication, the fact that we use the star to declare a pointer, but then we use a star in a third way to dereference the pointer and go to the pointer, it's just confusing, honestly. But with practice comes comfort. Yeah? Good question. Do you, when you are using the ampersand operator to get the address of something, the onus is on you at the moment to know what you are getting the address of. Is it a string? Is it a char? Is it a bool? Is it an int? I wrote this code, so I know in line 6 that I'm trying to get the address of what is an integer. In line 8, you don't have to worry about that. Good question. Notice in line 8, I didn't tell the computer, other than the %i, what kind of address I'm going to. But I did already. In line 6, I told the compiler that p, now and forever, is going to be the address of an int. That's enough information in advance so that printf, or really the language C, still knows on line 8 that p is a pointer to an int. And that way, it will print out all 4 bytes at that address, not just part of it, and not more than those 4 bytes. Good question. Yeah, next to you. Do pointers have pointers? Yes, we won't sort of do this today by having pointers to pointers, but yes, you can use ***, and then things get in. I'm sorry. We won't do that today, and we won't do that often. In fact, Python, another language, is just a couple of weeks away. So hang in there. Almost there. Question back here? Was there? That was amazing. Good. More verbal feedback like that is helpful as we forge into the more complicated stuff. Other questions? Yeah. What's the point of printing the address? Like, sure. What's the point of doing this? If you don't mind, let's get there in a moment. This is not the common use case, just printing out the address. Like, who really cares? At the moment, we care only for the sake of discussion. We're soon going to start using these addresses. So hang in there just a little bit for that one too. But it will solve some problems for us before long. So let's actually just now depict what was going on inside of the computer's memory just a moment ago. So if I toggle back here, let me redraw my computer's memory, and let me plop into the memory n, which is storing in this program the number 50. Where is p in my computer's memory? Specifically, I don't know, and apparently it moves around each time I run the program. So for the sake of discussion, let's just propose that if 50 ended up at address 0x123, I don't know, p ends up over here at address, at whatever address this is here. But notice a couple of curiosities now. If p is a pointer, it's the address of something. So the value in p should be an address. And I've indeed written it as such, 0x123. And technically, there's not an x there. There's not a 0 there. There's not even a 123 there, per se. There's a pattern of bits that represents the address 0x123. But again, that's week 0. Don't care about binary day to day. So if this is p, and this I claimed was n, why is p so much bigger? Can someone conjecture here? Because it turns out whether n is an int or a char or a bool, which are different types, heck, even a long, it turns out that p is always going to take up 8 squares on the board. But why might that be? What might explain that? Yeah, thought? OK, fair. Maybe it's allocating 8 bytes because it doesn't know the type. Turns out that's OK, because an address is an address. It's really up to the programmer to use it as a string or a char or a bool. Other thoughts? OK, possibly. It could be that pointers have some complexity, like a \n or something curious like that, like we talked about for strings. Turns out that's not the case. It turns out that pointers nowadays typically are, but not always, are 8 bytes, aka 64 bits, because you and I, our Macs, our PCs, heck, even our phones, have a lot more memory than they did years ago. Back in the day, a pointer might have only been 32 bits, or even only 8 bits, way back in the day. But consider 32 bits, because that was the norm for some time. How high can you count roughly if you've got 32 bits? What's the number we keep rattling off? 32 bits is roughly 2 to the 32. So it's 4 billion. And I keep saying it's 2 billion if you do negative. But in the world of memory, there's a reason I keep saying 2 billion bytes, 2 gigabytes, because for a very long time, that was the maximum amount of memory a computer could have. Why? Because the pointers that the computers were using were only, for instance, 32 bits. And with 32 bits, depending on whether you allow for negatives or not, you can count as high as 2 billion roughly, or maybe 4 billion. But you know what? Your Mac, your PC, your phone could not have had 5 gigabytes of memory or 5 billion bytes of memory. You certainly couldn't have had what computers nowadays come with, which might be 8 gigabytes of memory, 16 gigabytes of memory. Why? Because with 4 bytes or 32 bits, you literally physically can't count that high, which means if I drew a picture of all of the memory, we would run out of numbers to describe them, which means like most of my memory would just be unusable. So pointers nowadays are 64 bits. Or 8 bytes. That's really big. I can't even pronounce how big that number is, but it's plenty for the next many years. And so we've drawn it that way on the board here. Now, let's just kind of abstract this away. Let's get rid of all the other bytes that are storing something or nothing else. And let's now start to abstract away this complexity, because the reality is, to your question earlier, what is this useful for, or do we actually care about these addresses? Generally, no. We're doing this so that you see there's no magic. We're just moving things around and poking around in memory. But what a person would typically do when talking about pointers would literally be to just point at something. Like, I really don't care what address n is at. So it suffices in general when drawing pictures on a whiteboard, having a discussion with another programmer, you just kind of draw an arrow from the pointer to the value in question, because neither you nor I probably care about the specifics of OX whatever. So there's your pointer. It's literally an arrow. And we can kind of see this. So it turns out that these pointers, these addresses, are not that dissimilar to what we've done for hundreds of years in the form of a postal system. For instance, here's a post office. Here is a mailbox. And suppose that this is a mailbox labeled P. It's a pointer. And suppose there's another mailbox like way over there, which is just another byte of my computer's memory. What are we really talking about? Well, you store in a computer's memory values like the number 50 or the word like hi inside of your computer's memory at some location. But today, we can also use those same memory locations to store the address of things. For instance, if I open this up here, and I see, OK, the value inside of this mailbox is not a number like 50. It's actually an address, OX123. That's kind of like a pointer, sort of a breadcrumb leading from one location in memory to another. And in fact, with someone who's seated roughly over there, do you mind getting the mail over there? Volunteers over in this section? Just need you to get to the mailbox before I do. Who's being volunteered? Oh, yes, please. Whoever is gesturing most wildly. Come on down. Sure. What's your name? Say again? Anfu? OK, come on up to the edge of the stage there. And just to be clear, if this is P, that is apparently N. But to make clear what we're talking about when we're storing OX whatever values, like OX123, that's essentially equivalent to my, maybe pulling out something like this and just abstractly pointing to your mailbox there, or if you prefer, pointing to the mailbox. OK, all right. Oh, thank you. All right. This is akin to me pointing at your mailbox. And if you want to go ahead and open your mailbox and reveal to the crowd what's inside your mailbox, labeled N. All right. Thank you. We have a CS50 stress ball for your trouble. Thank you for coming up. So that's just to put a visual on what it is we're talking about, because it can get very abstract, very cryptic quickly when we're talking about addresses and memory and drawing it like these little squares. But if you think about just walking into a post office or an apartment complex that's got a lot of mailboxes, those mailboxes essentially are a big chunk of memory. And each of those mailboxes has an address. This is apartment 1, 2, 3, apartment 2 billion. And inside of those mailboxes can go anything that can be represented as information. It could be a number like N or 50, or if you prefer, it could be a number that represents the address of another mailbox. And this is akin, really, if you've ever had an apartment or you and your parents have moved, to having a forwarding address. It's like having the post office in the US put some kind of piece of paper in your old mailbox saying, actually forward it to that other mailbox. That really is all a pointer is doing. At the end of the day, it's just a number, but it's a number being used in a different way. And it's the syntax that we've introduced, not just int, but int star, that tells the computer how to treat that number in this slightly different way. All right, any questions then on this? Yeah, in back. If I did int c and set it, can you say the code again? Once more. Equal to n. So let me actually type it out. If I give myself another line of code, tell me one last time what to type. Int is equal to n like this. So this is OK. And I can't draw it quite quickly enough on the board here. But this would be like creating another 4 bytes somewhere in memory, maybe down here, that stores an identical copy of 50, because the assignment operator from right to left copies one value to another. So that would just add one more rectangle of size 4 to this particular picture, if I'm answering your question as intended. OK, so that is sort of week 1 style use of assignment operators before pointers. I could, though, start copying pointers. But again, we'll come back to some of that complexity. Any other questions here? Good question. Short answer, no. To repeat for the camera, if I create a second variable like this, int c equals n, And I claim, without actually drawing it on the board, that this gives me another rectangle, the value of which is also 50. P does not get touched. And this is what's important and really characteristic of C. Nothing happens automatically for you. Like P is not going to be updated unless you update P in some way. So creating a third variable called C, even if you're copying its value from right to left, that has no effect on anything else in the program. Good question. So what have we seen that's perhaps now a little more explainable? Well, recall that we talked quite a bit last week about strings. And just to recap, in layperson's terms, like what is a string as you now understand it? Let me take a specific hand here. What's a string? How about over here? Okay, sure. Both of you are right. An array of characters. An array of characters. And I claimed or revealed last week that string is not technically a feature built into C. Like it's not an official data type, but every programmer in most any language refers to sequences of characters, words, letters, paragraphs, as strings. So the vernacular exists, but the data type doesn't typically exist per se in C. So what we're about to do, if you will, for dramatic effect, is take off some training wheels today. The CS50 library, implemented in the form of that header file, CS50.h, we claim has had a bunch of things in it. Prototypes for getString, prototypes for getInt, and all of those other functions. But it turns out it also is what defines the word string in such a way that you all can use it these past several weeks. So let's take a look at an example of a string in use. Here, for instance, is a tiny bit of code that uses the word string, creating a variable called s, and then storing quote-unquote high exclamation point. Let's consider what this looks like now in the computer's memory. I don't care about all the other bytes. Let's just focus on these. And this, per last week, is how high might be stored. HI exclamation point, and then one more, as someone already observed, that sentinel value, that null character, which just means 8 0 bits to demarcate the end of that string, just in case there's something to the right of it. The computer can now distinguish one string from another. So last week, we introduced this new syntax. Well, if strings are just arrays of characters, you can then very cleverly use that square bracket notation and go to location 0 or 1 or 2, which are kind of sort of like addresses, but they're relative to the string, right? This could be at OX123 or OX456. But with this bracket notation, 0 is always the beginning of the string, 1 is the next, 2 is the next, and so forth. So that was our array syntax for indexing into an array. But technically speaking, we can go a little deeper today. Technically speaking, if high is starting at the address OX123, then it stands to reason that I is at OX124, exclamation points at OX125, and the null is at OX126. Now, I don't care about 123 per se, but even though this is hexadecimal, this is correct math. Even in hex, if you just add 1 when you start at OX123, the next number is 4, 5, 6 at the end. I don't have to worry about A's, B's, and C's because I'm not counting that high in this example. So if that's the case, and my computer is actually laying out the word high in memory like that, well, what exactly is S? Right? What exactly is S if at the end of the day, HI exclamation point null are stored at these addresses? Like, where is S? Like, now that I've kind of taken off those training wheels and showed you where HI exclamation point null actually are, what happened to S? Well, S, as always, is actually a variable, right? Even in the code I proposed a moment ago, S is apparently a data type that, yes, doesn't come with C, but CS50's library makes it exist. S is a variable of type string. So where is S in this picture? Well, it turns out that S might be up here. Again, I'm just drawing it anywhere for the sake of this discussion. But S is a variable per that line of code. What S is storing, apparently, I claim, is OX123. I actually don't really care about these addresses, so let's abstract that away. S is apparently, as of now, today, 1 week later, just a pointer to a character, specifically the first character in S. And this is kind of the last piece of the puzzle. Last week, we had this clever way of demarcating the end of a string. Well, it turns out that strings are represented in the computer's memory as a variable that is a pointer, inside of which is the address of the first character in the string. So if S is points at the first character, and you can trust that \0 is at the end of the string, that's literally all you need to figure out where a string begins and ends. So what do I mean by this? Well, let's be a little more concrete. In terms of this picture,
बोल बारिक
क्या कर रहा
कुछ नहीं बोलना
ऐसे ही फोन किया
पढ़ रहे थे